Hi, this is Mr. Bradley, and I am here to talk to you today about the concept of impulse. In this unit, we've been studying the idea of momentum, which is that when something is moving, it has mass and velocity, and then it has a property about it called momentum. And we've talked a lot about the law of conservation of momentum, which says that in the interaction between two or more objects, that the total momentum in a system always remains the same. But sometimes in a system, momentum does change, and when it does change, then we are now talking about the idea of impulse. When we look at our notes right here, we have a note that basically says in order to stop an object with momentum, it must take a force to do that. In order to make an object lose the momentum that it has, or even for that matter, in order for an object to gain momentum, you have to be able to apply a force to that object for that to happen. And that's where the idea of impulse comes into play. Okay, so impulse is essentially really just a change in momentum. That's really just the definition of impulse. For that reason, there is no letter per se for impulse. It's not like the capital letter I like you might expect it to be, but it literally is just delta P meaning change in momentum. Change in momentum can be calculated two ways. You can take force times time, or you can either take mass times change in velocity. We'd want you to recognize that either one of these equations will yield the units of momentum. Force times time would be newtons times seconds, which is one of the units that we can use for momentum, or mass times change in velocity would yield the units kilograms times meters per second, which is also the unit of momentum. Either one of those will help you get to the idea of impulse. Well, since both of these things equal delta P, you can set them equal to each other, and that's what we have down here. What we have down here is basically saying that impulse, or change in momentum, is equal to force times time, and that can also be equal to mass times change in velocity. This relationship right here is called the impulse momentum theorem. And the impulse momentum theorem is really just an easier way to look at forces where you don't have to directly solve for acceleration. There's a lot of problems that we've done in this class that probably would have been easier solved had we used the impulse momentum theorem. Let me show you an example of one of those kind of problems. The example that we have here in the notes says what average force is required to get a 1 kilogram hammer moving with a speed of 25 meters per second if the force is applied for 0.05 seconds. This is a problem that normally in the past we might have encouraged you to find the acceleration first and then use Newton's second law to solve for the force. But now we can just do it in one step. And let me show you what that's going to look like. I'm going to zoom in on this a little bit closer and do the work right down below here. So realize that the numbers that we have given in this problem, we know what the mass of the hammer is. It's 1 kilogram. We know that the change in velocity of the hammer is going to be 25 meters per second. Understand that the hammer is going to start off with an initial velocity of 0. It's going to end up with a final velocity of 25 meters per second. So the change in velocity is 25 meters per second. The time that it will take to do this is 0.05 seconds. If we use the impulse momentum theorem, which says that force times time equals mass times change in velocity, and we simply just rearrange this for force, we get this equation, mass times change in velocity over time. And I have all those numbers right there. I can just plug those numbers into the equation, and I can solve for what the force is. So 1 kilogram times 25 meters per second divided by 0.05 seconds. And when I do that on my calculator, I'll get 500 newtons. So the answer to this problem is 500 newtons. Okay, that's a simple way of how we use the impulse momentum theorem to solve problems. Okay, the idea of impulse is really very easy. It's just that the change in momentum can be related to force, time, or mass and change in velocity. One of the interesting things that you can do with the concept of impulse is when you apply it to a situation where a force is being applied to an object. So if you consider this simulation of a man applying a force on a box as he pushes it across a surface, I'd want you to imagine that he is applying a constant force over a period of time. When he does that, the graph that he would make might look like this. Okay, this graph essentially just shows, a constant force acting on an object as time goes by. Well, if you think about it, you could find the change in momentum by taking the value of this force and multiplying by the time over which that force occurred. So you would be taking this force times this time. The very interesting thing about that is when you take force times time, you're essentially also finding the area of this geometric figure that you found right here. A very, very important concept here is that the area under a force time graph is impulse. Now, what I'm introducing you to here is a calculus concept that's probably above what most people are going to be able to do in physics right now. But I can tell you that if you go on in life to take a lot more physics, you're going to find out that these kind of calculus concepts are highly important. Okay, so the final place that this is going to lead us to is looking at this kind of analysis. So what we're going to be watching right here is a video. It's a slow motion video, unfortunately, of a guy who is standing on a force plate. So the plate that he's standing on is basically measuring the force that he's exerting while he's going to go through a jump. So what I want you to notice is that he's dropping his body. You can see that the force is decreasing, but then as he slows himself down at the bottom, the force increases, and then as he goes to leave the plate, you can see that the force is continuing to increase. It's got a little dippity-doo in there because he's got a strange motion. But then notice as soon as he leaves the ground, as soon as he leaves the plate, that force drastically decreases and essentially goes down to zero because he's no longer pushing on the force plate. The idea from this whole thing is simply that in this region right here, you're able to see the force that he's exerting over time, and that changing force is typically very hard to analyze. But knowing what we just learned about the area underneath a force time graph, we can actually apply this to find out what the man's change in momentum is. Let me illustrate that to you on the graph underneath the video camera. Okay, so the graph that we're looking at right now is really a modified form of the one that you saw before. This is still a force time graph where you can see the force versus time, but now we just reset the scale so that we're really reading the net force. So the idea is that when the man was just sitting at rest on the scale, we're reading what basically like a net force equal to zero, if you will. And then as he dropped his body, that force actually decreased again, just like we saw, but now it's below zero. And then it goes up above as he's pushing himself up. And then as soon as he leaves the plate, you can see that that force drastically decreases down to the point to where he was not on the scale anymore. So essentially this value right here really reads like the negative weight of the man. This graph corresponds exactly to what you saw in the video that I pulled up from YouTube. So anyway, the idea being now that this shaded in region represents the area that's bound by the curve, and that area represents the man's change in momentum. What you can do with that is you can use that to figure out essentially like what velocity that you jump with, and that velocity will then allow you to figure out how high you jump. So this is an activity that we did in class, and if you haven't had a chance to do that, you need to come in and see your physics teacher so that you can create a graph like this of your own jump. We'll just use our force plate, and we'll graph you jumping off the plate, and you can use this idea to find the height that you jump. Okay, well, anyway, thanks for tuning into this video, and I hope it was helpful for understanding impulse and momentum concepts.